ever-present threat to life, property, and job security. Every year, industrial fires kill and injure hundreds of people, destroy millions of dollars of property, and wipe out thousands of jobs. The statistics are grim, the potential for disaster always there. In 1974, 28 people were killed when a fire and explosion completely destroyed the Nipro Chemical Company in Flixborough, England. The tragedy occurred when a bypass pipe ruptured, allowing a huge cloud of cyclohexane vapor to escape. The vapors drifted downwind until they contacted the source of ignition at a nearby hydrogen plant and exploded. The initial explosion was responsible for most of the deaths and also destroyed 90% of the plant. The blast at Flixborough is a chilling reminder of what can happen when things go wrong. Both human error and equipment failure were responsible for this disaster. But is there anything that you can do to prevent tragedies like this from happening at your plant? You bet. You can start by learning what fire is and how it behaves. Then you can use this knowledge to identify fire hazards and appropriate firefighting techniques for your own particular plant. You'll want to learn what kinds of fuel are present in your work area and what are the most likely sources of ignition. You'll also need to know how these fuels burn and how you'll control or extinguish fires involving them. Knowing the answers to these types of questions will go a long way in helping you prevent or minimize fire damage in your own work facility. And preventing fire damage is really what this program is all about. Let's start by taking a look at fire chemistry. This is a good place to begin because fire is really nothing more than a series of chemical reactions. The name given to these reactions is oxidation. Oxidation is a very common chemical reaction. When you place a nail in a container of water, it will slowly rust or corrode. This is an example of slow oxidation. Fire, on the other hand, is the process of rapid oxidation. Fire occurs when fuel, oxygen, and a source of ignition are brought together at the same time and in the right proportions. These three ingredients make up what's called the fire triangle. If any side of the triangle is removed, the fire dies. Although the fire triangle represents how ignition takes place, it doesn't totally explain why a fire continues to burn after it's started. In order for a fire to sustain itself, a chemical chain reaction between the fuel and air must occur. This chain reaction adds a fourth side to the fire triangle, changing its shape into a pyramid. Let's take a closer look at the basic ingredients of fire. The oxygen needed for combustion is readily available in our atmosphere. A lit candle, for example, burns freely as long as it's exposed to the air. But if a jar is placed over the candle, the flame will go out as soon as the available oxygen is consumed. Some materials like magnesium and unprocessed cotton contain oxygen within their chemical makeup. These types of substances may be capable of burning in an atmosphere that's void of oxygen. A second ingredient of fire is a source of ignition. Ignition sources provide heat energy that's needed to start the combustion reaction. The most common sources of ignition are open flames, hot surfaces, and electrical, static, or frictional sparks. Chemical action within certain types of materials can result in spontaneous ignition. For example, slow oxidation can cause a pile of oily rags in a closed container to gradually heat up. If the heat is not dissipated, the rags may eventually ignite. The third ingredient needed to start a fire is fuel. In most industrial settings, there are abundant sources of fuel, such as wood, plastics, chemicals, and fibers. And there are many common hydrocarbon products like gasoline, paints, solvents, and gases. Fires are often classified according to the type of fuel that's burning. Fires that involve ordinary combustibles like wood, cloth, and paper are given a Class A rating. Class B fires are fires that involve flammable liquids and gases. When energized electrical equipment is associated with the fire, a Class C rating is used. The fourth and final classification is for fires in combustible metals like sodium and magnesium. these types of fires are given a Class B rating. In this program, we're going to focus on Class B fires, fires that involve flammable liquids and gases. First, we'll look at the characteristics that affect how these fuels burn. Then we'll consider the firefighting agents and methods that can be used to extinguish Class B fires. Let's start by looking at the properties of a typical Class B fuel, gasoline. When gasoline is exposed to the atmosphere, it releases flammable vapors. You may have noticed these vapors before when you added gas to your car on a hot day. If a Class B fuel like gasoline is ignited, it's the vapor and not the liquid which actually burns. This holds true for all flammable liquids. The fuel must be in a vapor state in order for combustion to occur. Some liquid fuels release flammable vapors more readily than others. Fuels like gasoline, jet fuel, some crude oils, and alcohol will readily vaporize at ordinary temperatures. These types of fuels are considered volatile liquids. Other types of Class B fuels do not release flammable vapors until they're heated. Fuels like kerosene, fuel oil, lube oil, and asphalt fall into this category. These fuels are called non-volatile liquids. Because of their tendency to vaporize at normal temperatures, volatile liquids are considered more dangerous than non-volatile fuels. Flammable gases are another type of Class B fuel. Examples of these are hydrogen, natural gas, propane, and butane. Because these fuels are normally in a gaseous state, they always pose a serious fire hazard. Another requirement for combustion of Class B fuels is that fuel vapor and air be mixed in the right proportions. For example, if a spark is applied too far from the surface of the gasoline in this beaker, ignition won't occur. There's not enough fuel vapor to support combustion. The vapor-air mixture is said to be too green to ignite. If the spark is applied too close to the surface of the gasoline, we get the same result, no fire. Now there's too much gasoline vapor and not enough oxygen to support combustion. The vapor-air mixture is too rich to ignite. A fire will only occur when the spark is applied in an area that has the right proportion of fuel vapor to air. For gasoline, any mix ranging from 1% to 7% vapor in air is ignitable. If the vapor-to-air mixture is above or below this range, it won't burn. You can see from this chart that different fuels have different flammable ranges. A fuel like hydrogen has a much greater flammable range than kerosene. This means that hydrogen will be easier to ignite and therefore will pose a greater fire hazard. Let's review in more detail the material on the chemistry of fire and the properties of Class B fuels. In this segment of the program, we'll examine some more of the characteristics of Class B fuels, which affect how these substances ignite and burn. You already learned that three things are necessary to start a fire: fuel, air, and to source ignition. These three ingredients must be present at the same time and in the proper proportions. You also learned that the fuel must be in a vapor state in order to burn, that some fuels produce vapors more readily than others. The tendency of a liquid to produce vapors can be measured under standardized conditions. This measure is called vapor pressure. Different types of fuels have different vapor pressures. Under standard atmospheric conditions, propane produces more vapor than butane, so propane has a higher vapor pressure. Vapor pressure is directly related to temperature. When the temperature of a liquid increases, more vapors are formed, which causes a corresponding increase in vapor pressure. This is the reason why a fuel that's relatively safe at low temperatures can become highly flammable after being heated. The additional heat generates enough vapors to form a flammable mixture. Vapor pressure is important because it determines the composition of the vapor-air mixture over the surface of a liquid. When this mixture is within the flammable range of a fuel, the only element missing from the fire triangle is a source of ignition. Another important characteristic of a fuel is its flash point. Flash point is the temperature at which a liquid gives off sufficient vapors to form a flammable mixture. Gasoline has a very low flash point, somewhere in the neighborhood of 40 degrees below 0 Fahrenheit. So, whenever gasoline is above this temperature, it will release ignitable vapors. The flash point of kerosene, on the other hand, is around 120 degrees Fahrenheit. At room temperature, a beaker of kerosene will not ignite because the mixture of fuel and air is too lean. But if the kerosene is heated, its vapor pressure will start to rise, and the amount of vapor in the area above the liquid surface will gradually increase until the flammable mixture is reached. The flash point of any fuel can be precisely identified with a flash point tester. This is very useful information because it tells us the exact temperature at which a fuel will release ignitable vapors. At ordinary temperatures, fuels with low flash points present the greatest fire hazard. But when any substance is heated, it will eventually produce enough vapors to present a fire hazard. Since it's the vapors which actually ignite and burn, it's important to understand how these vapors move or travel after they're formed. The most important characteristic that affects the movement of a vapor is its density. The density of a vapor is simply its weight compared with the weight of an equal volume of air. Hydrogen, for example, is lighter or less dense than air. If hydrogen is released into the atmosphere, it will quickly rise upward and disperse. Since the hydrogen moves rapidly upward, it's unlikely to contact a source of ignition once it clears the area of the release. The situation would be much more dangerous if the hydrogen release occurred in some type of confined area. Most fuels produce vapors that are heavier than air. When these types of vapors are released, they will tend to cling to the ground and gradually move downwind and downhill, seeking low areas. If enough fuel is released, a vapor cloud may be formed. Vapor clouds are extremely dangerous because they can travel a considerable distance without being dispersed. If a flammable mixture is present, the cloud may be ignited by any nearby source of ignition. Gasoline is one type of fuel which produces vapors that are heavier than air. We can demonstrate this point by saturating a cloth with gasoline and then placing it in the top end of a vapor tube. The gasoline vapors will gradually flow down the tube and make contact with the flame at the other end. The vapors ignite and then flash back to the cloth pad. Let's look at the vapor characteristics of two other common industrial fuels, LP gas and natural gas. LP gas is primarily composed of propane and butane, which are both heavier than air. Normally, LP gas is stored in sealed, pressurized containers where it's relatively safe. But if a gas leak occurs, the vapors will hang near the ground and are slow to disperse. This type of release presents a serious fire or explosion hazard, especially if there are any sources of ignition in the vicinity of the spill. Natural gas is another widely used fuel. Its composition is mainly ethane and methane, which together are lighter than air at normal temperatures. Natural gas, however, is usually stored as a liquid at very low temperatures. These low temperatures increase the density of the gas, making it heavier than air. So a release of natural gas can form a large vapor cloud that's slow to disperse. Let's take a look at some of the properties of liquid fuels that affect their burning characteristics. Specific gravity is the measure used to determine the relative weight of a liquid fuel. The specific gravity of a liquid is its weight compared to the weight of an equal volume of water. Most flammable liquids are lighter than water, which means they'll float on top of it. Suppose we put water and gasoline into the same container. The gasoline will rise to the top because of its lower weight. We can ignite this sample of gasoline, and it'll burn freely until the supply of fuel is exhausted. Since most liquid fuels are lighter than water, care must be exercised when applying water to these types of fires. If hose streams are improperly splashed into the fuel, the additional water may only serve to spread the fire. The majority of flammable liquids are not water-soluble, meaning they will not mix with water. There are, however, a few Class B fuels like alcohol and ketone that dissolve in water. These are called polar solvents. Because polar solvents are water-soluble, water can be used to dilute these types of fuels. In the next section of the program, we'll be looking at extinguishing methods. Before we move into this area, however, we'd like to review the material on the characteristics of Class B fuels. In this segment of the program, we'll be taking a look at the methods that can be used to extinguish a fire and the various extinguishing agents that are available for fire suppression. Any fire can be extinguished by removing one of the four sides of the fire pyramid: heat, oxygen, fuel, or the chemical chain reaction. Fires can be extinguished by smothering. To smother a fire, you deprive it of the air or oxygen it needs to burn. A fire can also be stopped by cooling the surface of the fuel below its flash point. Cooling the surface of the burning fuel retards the formation of vapors, and when the vapor-air mixture becomes too lean, combustion will stop. This method of extinguishing a fire is called quenching. The third method of extinguishing a fire is starving. A fire is starved by cutting off the source of fuel which is feeding it. The fourth and final method of extinguishing a fire is to break up the chemical chain reaction that occurs between the oxygen and the fuel. This is known as inhibiting. A fire cannot sustain itself when the chain reaction has been inhibited. So there are four ways to extinguish a fire: smothering, quenching, starving, and inhibiting. But which is the best method to use, and how is each accomplished? Water is the primary firefighting agent for cooling or quenching a fire. When water is applied to a fire, much of it is vaporized to steam. This blanket of steam helps to exclude oxygen from the fire. So in addition to cooling, a spray of water also smothers the fire. Although water is an outstanding coolant, it's ineffective on fires that involve fuels with low flash points. Gasoline has a very low flash point, somewhere in the neighborhood of 40 degrees below zero Fahrenheit. If water is applied to burning gasoline, the fuel will continue to release flammable vapors. So normally a gasoline fire cannot be extinguished by cooling. Another important firefighting agent is foam. Although there are several different types of foam, all of them are made up by mixing water with a special foam concentrate. When foam is properly applied to the surface of a burning fuel, it forms a vapor seal. This seal prevents air from reaching the fuel, and also prevents fuel vapors from reaching the fire. Because foams are made with water, they also cool the surface of the fuel. So foams put out a fire by a combination of three extinguishing actions. These actions are smothering, starving, and quenching. For foams to be effective, however, the surface of the burning fuel must be relatively flat. There are certain types of fuel that foam should not be used on, such as flammable gases. Fuels like LP gas have a very low boiling point and will continue to vaporize underneath a blanket of foam. These vapors are light enough to bubble up through the foam and continue burning on top of it. A third type of extinguishing agent is CO2, carbon dioxide. When carbon dioxide is applied to a fire, it dilutes the oxygen content of the air down to a level that will not support combustion. So carbon dioxide is a smothering agent. While carbon dioxide is effective on nearly any type of fuel, it loses much of this effectiveness outdoors, where the wind can disperse it before the fire is extinguished. For this reason, CO2 is primarily used for fighting fires in enclosed areas. When you enter areas that have been flooded with CO2, it may be necessary to wear specialized breathing equipment. This is because the oxygen content of the air may be too low to support human life. One disadvantage of CO2 is that it does not extinguish most sources of reignition, such as hot ashes or glowing embers. This problem, however, can be overcome by spraying any embers or other possible sources of reignition with water. Dry chemicals are a fourth type of extinguishing agent. These are chemical mixtures that interrupt the chain reaction of combustion. When the reaction is halted, the fire goes out. Dry chemicals are available that can extinguish Class A, B, and C fires. These chemicals, however, are not normally used on sensitive electrical equipment because they leave a residue which is difficult and expensive to remove. Another limitation is that dry chemicals don't extinguish smoldering embers and other potential sources of reignition. So water is usually applied before or during the application of chemical to avoid reignition of the fire. The fifth type of extinguishing agent we'll look at is halogenated agents or halons. These are special liquids or gases that work chemically to extinguish a fire. Halons, like dry chemicals, break up the chemical chain reaction of combustion. Halons are effective for fighting flammable liquid and gas fires as well as most fires involving solid combustible materials. They're especially good for fighting electrical fires because they don't conduct electricity and they leave no residue on sensitive parts. The last group of extinguishing agents are dry powders. These are finely divided powders that are specifically designed to fight combustible metal fires. When a powder is applied to a fire, it forms a crust that excludes oxygen and smothers the flames. This concludes the audio-visual portion of the program. In this program, we introduced you to some general fire chemistry, and we focused on those fires involving Class B fuels. We learned about the characteristics of these fuels and how these characteristics affect the way a particular fuel burns. And finally, we looked at the firefighting agents and methods that are used to extinguish Class B fires. We should have a better understanding now for just what fire is and why the properties of different fuels determine what types of firefighting agents and techniques will be effective on any given fire. This type of information is important because it will help you to maintain a safer work environment.
إذا كنت من المتابعين الجدد اشترك الآن في القناة ليصلك الجديد بالضغط على الزر الأحمر أسفل القناة مع تفعيل الجرس، ولا تنسوا دعم المقطع بلايك. شكرا لكم جزيل الشكر.